Okay, so let's come to the first impossible machine that I want to tell you about. I call it the classical translator. And that would be a device that generates from a quantum particle a classical description. So in some sense you could say it translates quantum information given in the form of quantum particles to classical information, the sort that you could print, and then of course converts back, right? So the whole thing would look like this. Here you have a quantum particle coming, and so the straight arrows correspond to classical information in these pictures now. And so you have a conversion from quantum to classical to quantum information. So actually this conversion is just a fancy way of saying that you have a measurement. And this guy, of course, is a preparation because you're generating a new quantum system, but it depends on the parameter. So let me call this the re-preparation or the reconstruction, right? And so it's important that in the middle we have classical information. Classical information. Like any old measurement result, right? So the sort that you can print. Okay. So of course, now you could do something like that, right? You can make a measurement and then you can re-prepare something. The whole point is that this should be equal to doing nothing. Right? Now, this equal is something that I have to explain, and it will come up several times. Right? So, what is our criterion for equality here? So that means, so this is no change. That means that no change in any statistical experiment. So it's certainly not that the same particle comes out at the end. Right? That's not too much to ask because the first measurement typically destroys the particle anyway. Right? So it's not about the individual case, but it's about making combined experiments now with an arbitrary preparation here and an arbitrary measurement at the other end. And I use the same preparation and the same measurement just directly. And then if I don't see any change in the probabilities, I say this is a good translator. Okay? So you could think of this as, in the double slit situation, this would be a way to extract from the quantum particles a classical description. And it doesn't really have to be physically a device that does that. So it also can be in a thought experiment. So a way to extract a classical description, if you want to use it in this operational way, then it would actually be a device doing that. And from that classical description, you generate the particle again. And the criterion for the whole thing is that you wouldn't know the difference by statistical measurement. Right? So this is what I call the classical translator. And it's an impossible machine. And actually, it's the reason why we even talk about quantum information, because we cannot just convert it to classical information. So the classical information theory by Claude Shannon was immensely successful because of this abstraction that a bit is a bit and you don't care how it's realized. Now, if quantum information could also be written in terms of bits, there would be no need for a field of quantum information theory, right? Because you could just convert it to classical. Also for the theory, I mean, you could work with these descriptions instead. So that if that is an equivalent representation. But the claim is it's not. Right? So this is impossible. Right? So this is impossible. And now comes the proof. So, and I will prove it, and there will be several steps of this kind. I prove it by reduction to another machine, which is also impossible. Okay? So there will be actually a sequence of such impossible machines, and if I have one, I can maybe build the other. So this is the relation between the machines, and in the end, you'll see that the whole bunch is impossible. So that will be the proof for the whole impossibility of all this, including this classical description. Okay, so next machine. Okay, so here's my second impossible machine. It's called the cloning machine. So let me first explain what it's supposed to do. Right? So we have a quantum particle, right? And the cloning machine, maybe put a C in it for cloning, has two outputs. Right? So it produces two systems of the same kind. And now you can do that, of course. You can make machines that have this kind of input-output behavior. But the point is that each of the clones is as good as the input. So actually, if I do this, I'll take the cloning machine, I make a measurement on this guy, maybe a preparation here, right? So preparation P and a measurement M. And here I just discard that particle, right? So maybe think of this as a wastebasket. I'm just not ignoring this, this goes out the window, right? Then I can compare that with another experiment where I just do the preparation, same preparation. I leave out this whole crap in the middle and just make a measurement. And this equality here again says same probability. Okay? So the criterion for success here is also statistical, right? This will be true of all the examples that I give, right? So you only check that this works on average, right? So, but then for arbitrary preparations and measurements, you should get the same. And of course, I didn't write this now, but it's clear that I demand the same of the other output. Right? So both outputs are statistically equivalent to the input. And that means that if I make experiments with that, I wouldn't notice the difference. Right? So I claim that this is impossible. Well, it isn't. We'll see that it's impossible. But my point is that I could build this from a translator. So if I had machine number one, that is the classical translation machine, then I could make this. Now let's see how that goes. Right? So I have the classical translation machine, and it would make the measurement, and that would produce some classical output. Right? And so I could take this classical output and copy it. So this is a classical copy. Well, this is like printed text, so I can just print it twice, right? And then I just buy two versions of this reconstruction apparatus, this repreparation. Right? So now let me just take this whole thing as one new device. What does it do? Now, according to the description of the translation machine, it's clear that if I take this is a faithful translation. So I get the same statistics when I make measurements with this as I get for just a direct measurement. And the same is true here because it's a reconstruction device. But this is exactly the description of the clone. Right? So in this way, I can use the classical copying machine by just buying the reconstruction machine twice and make a cloner out of it. Okay, so now why is the cloning possible? There's something called the no cloning theorem, which is very famous, and I could cite that now. But then, in order to show that to you, I would need the whole formalism of quantum mechanics. I don't want to do that, right? So I do it. So impossible. So the cloner is impossible, and the proof by reduction. Same idea, right? So we'll get to our next machine, and in passing, we'll have proved the no cloning theorem. Okay, thank you. So here's the next impossible machine. I call it the joint measurement. Right? And the task in this case is that I have two measuring devices. Right? So let's call them, let's say M1 and M2. And I want to combine them. I want to do them both at the same time. Now, it's pretty obvious for most devices that I have, that it's impossible to do that directly by just applying the both machines. For example, one might involve the polarizer being set in a certain way, and the other might demand the polarizer be set in another way, right? I can't have both, clearly. I mean, then the two polarizers would be just being in each other's way. So it's clear that you cannot just combine the machines, right? Or the measurements, and just make them at the same time. But you might do something which is a clever replacement. Um, um, well, the joint measurement would do the following. You would have one machine, and it looks like this. It has, so let's say the output of this is called x1, and the output of this is called x2. Right? Could be different kinds of quantities. But now I have a joint measurement, which I call M1 and M2, which has two outputs, an X1 output and an X2 output. And what's the condition for that, right? Such that, well, if I just take my joint measurement device, I take the X2 output and I discard the second, sorry, this is X1, and I discard the second output, then the probabilities that I get would be the same as if I just use the first one, right? So again, this means statistical equivalence. So for an arbitrary preparation, I get the same probabilities. Okay, so that is a way to replace that. It might be a totally different device. So you really might need some ingenuity to build that, so that you have a way to work around the fact that the two polarizers can't be in the same position and would have to be in the same place. So you build something entirely different, maybe polarizing beam splitter and stuff around it and a big machine, whatever. But this is the criterion of success. So again, it's an impossible machine. But if I had this cloner, I could do it. Well, let's do it. Right? So a cloner will make this possible. So I have a little bit of space left here. So let's bring in our cloner. I think I called it C. Right? And so very simple. I get two outputs. I make measurement M1 on this. I make measurement M2 on the other output. That will give me an X2-like result and an X1-like result. And if I compare what I said about these machines and the criterion for their success, a successful cloner would automatically do this. In fact, you could say a cloning machine is nothing but a universal joint measurement device. Right? So it does it for arbitrary measurements. So now, how does this impossibility scheme go on? Well, I claim this is impossible again. Right? So the joint measurement is in general impossible. Of course, sometimes it is possible, but in general it's impossible. So this is an impossible machine. And now again, I could prove this by going to the quantum mechanics books. And actually, what students learn is that this property of joint measurability is very closely related to observables commuting. And the general structure in quantum mechanics, it's very easy to exhibit observables that do not commute, operators that do not commute as operators on the Hilbert space. So that is what you would need to prove this from quantum mechanics. But once again, I'm not assuming quantum mechanics here. So I want to use a similar sort of argument. So I will prove also this by reduction. So I'll come to one machine where, had I such a joint measurement for the devices that appear in a certain experiment, if I had that, I could do something else which is manifestly impossible. So this would be our final reduction step. And actually, it's the only one that cannot be simply done by just drawing a diagram. Right? So far, all this is actually rigorous. You can make, if you can formalize it and make proofs out of it, but I mean, formal proofs, mathematical proofs out of it. But the last one is a bit more difficult. So let's have a look at that one.